In this video lesson, I'll be showing you how to calculate acceleration from a non-uniform graph, still under velocity time graph. Non-uniform graph, that is, the graph is not a straight line. In the previous videos, I did show you how to calculate the slope of a straight line graph. That is, the slope of a straight line graph, that is, velocity time graph, represents acceleration. Now, suppose you are given a non-uniform velocity time graph. How do you go about calculating? Now you have to determine the acceleration from the graph. That is what I want to show you in this video, and I hope you get it clearly. Now this is my graph, looking at you there. Please don't laugh at my graph because I've been able to do some, been able to improvise my own graph. I'm sure if you get your own graph paper, you'll be able to do it very well. So mine just to explain it to you step by step how to calculate the slope of a curved graph. Okay, so the velocity axis is already labeled from 5, 10. Each of these is 1 cm. So my scale is 1 centimeter, representing 5 units, 5 meter per second on the vertical axis. And the scale for the time axis is 1 cm because this spacing is just 1 centimeter. So it's 1 cm representing 1 second on the time axis. Okay, and here's the table. I'm going to use this table to draw my graph. As you can see that at time t equals 0, the velocity is 0. When the body starts from rest, the graph is going to begin from the origin. After 1 second, the body is now moving at a speed of 7 meters per second. After 2 seconds, the speed has increased to 13. After 3 seconds, you can see the rate of increase is not the same. The difference here is just 6. For this time interval, the increase is just 5 meters per second, then this is 4. As time increases, the velocity is not increasing at a uniform manner or pattern or rate. So let's plot these values on our graph space. So at t equals 0, I plot it here because velocity is 0. So when time is 1 second, my 7 seconds is around here, or 7 meters per second is here. I plot here at 7. For t equals 2 seconds, the speed is 13. This is 10, 11, 12, 13. So I plot that against 2 around here. So for a time of 3, the speed was 18. This is 15. This is 16, 17, 18. I take that out, plot that against 3 seconds here. So when time is 4 seconds, 22 was the velocity. So this is 21, this is 22. I take this out. In your own case, you can use your ruler to trace out, of course, you trace this out and then that. Then for 5 seconds is 24. 24 is very close to 25, around here. For 6 seconds is 27. This is 26, 27. So use your ruler, take this out like this, and then plot it against 6 seconds. 27 here. And for 7 seconds, it is 29. Around here and so on. We are going to join these points using an instrument. You can decide to use a broomstick. You can use a French curve. Don't join it with your hands because it's not going to give you a straight line graph. From what you have seen here, this is a curve. Let me just try to join it with my free hand to give me something like this. A curve of decreasing, not decreasing speed. It's like the speed is approaching a constant value. So here they will ask you 1 or 2 questions. Number 1, want to determine the slope of the graph, determine the acceleration of the body. From your graph, you see determine the acceleration of the body at t equals 4 seconds. What is the acceleration of the body after 4 seconds? Or at time t equals 4 seconds from the graph. That's one question they can ask you from the graph after drawing. Or some they can just give you the graph like this and say, find the acceleration, because not every time you have to plot it, especially if it's objective, multiple choice questions. To give the already plotted graph and say from that graph, determine the acceleration at this specific time. Or at this particular point, which was at point, if they put this as point P, what's the acceleration at that point? You trace, of course, the same. This point P is same thing as 7 seconds later. So 4 seconds later, I come here. This is a point. Let me call this point A. And to find the body's acceleration at point A at time t equals to 4 seconds. What I'll do, step one, I'm going to draw a tangent. Draw a tangent at point A where time t equals 4 seconds. What's a tangent? It's a straight line that touches a point on a curve, on a curved line. It touches a point on a curved line. That is a tangent, a straight line. So I'll place a tangent at A carefully with my ruler, not with a free handle, the ruler. You can extend the tangent the way you want it. That's my tangent at A. That is step one. Step two, you can choose 2 points. Choose 2 points on the tangent and then use the 2 points to draw your slope triangle and then draw a slope triangle at that I've been using the 2 points on your tangent. Okay, so I'll come back to my tangent. This point must be a point that you can easily interpolate. You can easily get values or easily interpolate the coordinates of the point, a value on the velocity axis and get the value on the time axis. So do not take a point that falls within a square box, such as a point. Okay, let me just say at that point I have, let me see, for instance, if you have something like this, you have this other 0.1 or 0.2 cm square line. So do not take a point that is within this box, for instance, a point such as this is within the box, is within. Choose a point that lies on the grid lines of your graph space for easy interpolation. So I'm going to take a point. I want to take this point. I'll call that point 2. And then I'll take this point. I'll call this point 1. Let's assume that this point is exactly on this point on my time axis. So this my point is point 1, and here I have point 2. On the tangent, then I draw my vertical and my horizontal. What I'm drawing here is my slope triangle. Then I get this as my change in V. Then evaluate my change in T. Okay, so that then calculate step 3 says draw the slope triangle and then calculate the slope using the slope triangle. So that my slope is change in V by change in T. So I'll come to point 2. My V1, my V2 rather is 30 minus, come to point 1. My V2 is, this is 10, 11, 12, 13, 14. It's roughly 14 over, what's my T2? Come to point 2. Trace it down to the time axis. This is, so this may be 6.2, 6.4, 6.6, 6.8, and then 7. 6.246, 6.6, 6.6 minus, come back to point 1. What's my T1? This is my 1.2, 1.4, 1.6, 1.8, and then 2. 1.2, 1.4, 1.6, 1.8, and then 2. This is my point 1. Take it down to the time axis. That's 1.8. So that here now my slope, which is my acceleration, is equal to 16. That is this minus this. divided by 6.6. 6.6 minus 1.8 gives me 4.8. So that by the time I divide 16 by 4.8, that gives me slope of the graph at point. That gives me 3.3 to 1 decimal place. That gives the slope of the graph at point A. I mean, that gives the slope of the tangent drawn at A. And the slope of the tangent, finally, slope of tangent at A, point A, which is 3.3, is equal to the slope or the acceleration or slope of the graph at the same point A. So the slope of the tangent at A, which is this straight line I drew, touching point A, is equal to the slope of the curve of the non-linear velocity time graph at the same point. And since the slope is acceleration, I can say that the acceleration of the body therefore is equal to 3.3 meters per second squared. That is how to calculate or determine the acceleration from a non-linear velocity time graph. How about if it has to calculate the distance traveled from the same graph, distance covered? Recall I said distance covered is given by the area, is calculated, is determined from the area under the graph. Let's say distance covered in 4 seconds still. This is my 4 seconds. Okay, so meaning I want to find the area bounded by this ordinate, the time axis, and this curve. Now, since it's not a straight line, there are two or so methods you can use to determine or to find the distance covered in a given time. One method is a method of counting squares. Method of counting squares. Now, how many 1 by 1 square present? This is 1, 2, 3, 4, 5. This is the curve I'm talking about. I'm referring to this curve here. Let me make it bold. This is a complete square. 1, 2, 3, 4, 5, 6 complete squares. So there are 6 complete squares. And the area of one square, area of one large square is, this is 1 by 5. Is 1 times 5, which is 5 meters. That's the distance covered within one square. Area of one full square. Area of 1 cm by 1 cm square. This 1 cm, this 1 cm. So this is 4 minus 3. That is 1 by, this is 0 minus 5. This is 5. So 1 times 5 is 5 meters. Recall that this is time. This is meter per second. So, and then we have 5 complete squares. 1 by 1 cm square. So that gives me, 6. 1, 2, 3, 4, 5, 6. That gives me 6 times 5. Already I've gotten 30 meters. But that's not all. We have to come back to the other squares that we didn't count. This one is part of it. We didn't count it because it wasn't a full square. This is not a full square. This is not a full square. Let me mark this one. Not a full square. This is not a full square. This is not a full. This is not a full square. 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 Then I can do some arrow and trial method. If you check very well, this one will have become a full square if I add this fraction to it. If I add this fraction to it, this small fraction to it, approximately equal to 1 square. So this and this will give me 1 full square. 1. Okay. That is, I'm taking this and this together because this one is what is left to make this a full square. So when I take this and add to this, it gives me a full square. Then this one appears to be half of a square, or this one and this are equal to, both of them can give me 1 square plus 1. Then this is roughly 1, or this small thing here added to this small space added to the give another 1 squared. That's another 1. Then finally, there's one I did not indicate. I've not marked. I think this one. Then this one and this one can give me another full square. So roughly I have about 4 squares and the area of one square is 5 multiplied by 5, that give me 20 meters. Area of one full square is 20 meters. So total distance traveled is 30 plus 20, which will give me 50 meters. Okay, so but if you don't want to do that, if you have a complete graph, after counting the areas of large squares, you can also use the idea of using small squares. Small squares. We have small squares in between. In between this 1 cm square, we have about 5 small squares. You can decide to count that one and multiply by the area of one small square. Then you call this one a large square, then you call this one a smaller square.